Okay, so what we did before we kind of started lecture here, for those of you just logging in or listening in, is we forgot to turn off the little thing that takes up the center of the screen. Is we wanted to come up with a set of rules that you guys have sort of internalized already, hopefully, for how to name organic compounds. And everyone's rules are going to differ a little bit. And, I'm going to put up a set of rules and I'll put down what you guys tell me and I'll put down some of my own stuff. But again, you have to decide, is my set of rules enough? Did I include enough things? Because, my set of rules personally is longest chain, side chain, something else, or numbers and then alphabet. Meaning those four things are enough for me to get all the details. But I practice this a lot. I do this enough that, I only need a couple gentle reminders. But you guys will maybe need a bigger set of rules to start with, and then as you practice more and more over the next bunch of chapters, you'll find that you need those rules less and less. So what's the first rule? Yep, longest chain. And what are some things we should remember about the longest chain? And I have to admit, some of these little sub-rules, especially since we've only started naming one thing so far, meaning alkanes, some of the extras that I'm going to throw in here you may not know yet, or you may not just think about because you haven't had to use them. But what are some extra things that we should remember about the longest chain? It's got to be continuous, right? And we only count carbon. And so when we start getting into things with nitrogens and oxygens, we won't count those as part of the longest chain when we're naming anything. Let's see. I suppose I should look and see where my notes were just to make sure I don't miss anything silly, but I think that pretty much covers the longest chain. What's the second thing you kind of do when you have the I'm sorry, one other thing. It has to contain the functional group. And since we haven't talked about any functional groups, every longest chain you've looked at has had that. And so those three little sub things there, for the most part, are things that you haven't had to deal with yet. And we'll worry about those next week when we start looking at how to name alkenes and alkynes and aromatic compounds. What would you say the second thing you would have to do is? Yeah, you have to number the longest chain. Now, what Owen said is find the side chains, and that's kind of long. Oops, I got an extra some letters in there. Longest is that you have to figure out your side chains, and you're kind of doing both at the same time, right? You're numbering, and then you're also paying attention to where the side chains are so that you can figure out that. So what are some rules for numbering the longest chain? Yeah, you want your side chains have to have the lowest number. And so, for instance, 2, 3, 4 is better than 3, 5, 7. Or 2, 8, 9 is actually better than 3, 4, 5 because we really only look at that first place, right? And then if I have something like, say, 2, 2, 3, well, that's equal to something else that has 2, 2, 3. So we have to remember, what's our tiebreaker? Yeah, tiebreaker is alphabetical. The other thing I might do if I were you guys is write down an example of each of these processes too, meaning write down, say, can I think of a molecule that has the same numbering, but I have to decide which way to go from. For instance, in this molecule, this illustrates the whole longest chain thing. It illustrates the numbering, and it illustrates that tiebreaker, right? So in this case, which end do I number from, left end or right end? What was that? It was like left or right? Yeah, I want to go 1, 2, 3, 4, 5, because then alphabetically this is a 2-chloro, which is better than a 2-methyl. because the 2 should go with the lower, or with the alphabetically the one first. And so we would call that, like, 2-chloro-4-methyl, methyl pentane. Okay, so this is where it's very easy to say the rules. For instance, it's great if you memorize these rules, but especially for this one, you really have to be paying attention to those rules and practicing using them so that you go, oh yeah, I know that the alphabetically the 2 should go with the chloro instead of the methyl, but if you don't do that in practice, then it's no good. Okay, what about, let's see, what's next? What are some other things that we should remember? What are some other things that you got wrong?
Like 2, 4, like where they are on the points for when you draw it out.
Right. So what you're saying is that if I'm going from a picture, or from a name to a picture. Okay, that's good, but we'll cover that next. So what are some other little things that we should remember? What if I have something like this? What's the tricky part of naming this molecule? Yeah, this is 2,2,3-trimethylpentane. And so that di-tri part, I have to be honest, that's the part that I think it's redundant in the naming to a certain extent, meaning it doesn't need to be there because I've got 3 numbers there, right? And so it seems like it's redundant, but it is part of the naming conventions, and so we are going to, enforce that. What are some other little things we need to worry about? I can only think of one more, and it's not necessarily something. Cyclo. Yeah, so you have to remember your cyclos. And maybe this is the miscellaneous category. So the miscellaneous category has the dis and the tris. We have to remember that we can have cyclos, and so that this is cyclohexane. And that if we have just one thing on it, that it doesn't matter where I draw that, they're all the same, and they're all methyl cyclohexane. Whereas if I have 2 things on them, then I do have to number, because I might have something like this where it's 1,2-dimethyl cyclohexane, and I might have something where it's, for instance, 1,3-dimethyl cyclopentane. So cyclos are one of those, I really do kind of consider it miscellaneous. You're not going to have a ton of them, but it's something that you've got to keep in the back of your mind. And then how about another miscellaneous one? Yeah, we're going to do that one next, after the one I just started writing. What should I call this? Not meth, but ethane, because we're saying that there's 2 carbons there. And notice, do I need the number there? Yeah, sometimes we leave the number off if it's redundant. And we saw that with the cyclo one, right? If I just have one thing on a cyclo compound, I get to leave it off, the number off, right? Because all positions are 1. They're all the same. Here, it doesn't matter which carbon I put that chlorine on, they're the equivalent carbons, right? Now, compare that to if I have it like this. Well, now I have to put the number, because now there's more than one spot to put that chlorine, right? I can have a 1-chloro or a 2-chloropropane. So sometimes we have the numbers, and sometimes we can leave them off in rare cases. And my theory is you're better off just always putting the numbers and occasionally getting one wrong than trying to leave the numbers off too many times. And Owen brought up a good point. Numbers are always separated by commas, right? Numbers and words are always separated by a dash. And you've probably already internalized that rule, meaning just by me doing the examples, I find that if I actually point that out and say it, it seems to confuse people more than if they just see 10 or 15 examples with that and then they start to kind of internalize it already. And what else have you guys already internalized that no one's brought up so far? So these are really things you already know to a certain extent, and you can kind of leave them off your list. Like I said, your list will get shorter and shorter, hopefully, over time, where instead of having 50 rules to try to remember, you're like, well, I already remember 49 of them. I'm only going to write the one rule down I forget, which is I always forget that stupid die, try crap. So what's another rule you've internalized? It's probably so internalized you can't even say it. Yeah, so you've internalized the meth and the eth part. Now, I have to admit, I saw some people when they're doing their homework having to look that up. That's fine. By the time you're done practicing this, 1 through 10 is going to be like 1 through 10 in any language. What else have you already internalized? Yeah, ain versus YL, right, versus the chloro for side chains, right? So you've already kind of internalized the difference between a main chain and a side chain, just because by practicing enough, you've gotten it, right? So realize that you already know a good chunk of this. And the rest of it, in order to internalize it, to make this list shorter and shorter, I can only say practice. I mean, it kind of bugs me to say, just practice. You know, there's nothing I can do to teach it to you. Well, at a certain point, there is nothing I can do. I've taught you the rules now. We've even covered them twice. I'm certainly more than willing to sit down with you and come up with other ways to remember them or things like that, to work through them, to practice. But you will not know if you know this material until you go and practice it. So go and print off those extra practice sheets and make sure you get 19 out of 20 on it. Go ahead and do the computer and say, I'm going to sit down, I'm going to, tomorrow's Saturday. I know it's a crappy day, but at some point on Saturday, I'm going to sit and I'm going to click that button 20 times and I'm going to practice naming stuff. And if I don't get 19 out of 20, set yourself a goal. Say maybe your first goal is not 19 out of 20. Maybe it's 15 out of 20. Hopefully it's more than 10 out of 20. I hope you're at better than the 50% point right now. But keep track of that too. Have a page in your notebook or something where you're keeping track of your daily progress on that. And then remember that we're going to learn to name 3 more sets of things, right? And so you've got to master this one sometime before next week on Wednesday, probably, when we move into the chapter 20 molecules and how to name those. So kind of think about it that way. Okay, so that's a good review, hopefully, on naming. It's not something that you pick up in one lecture, I don't think. And so that's why we're going to hit it time and time again. Jess, you had a quick question? You're just waving at me? Okay. Okay, so the rest of the topics I'm going to cover today fit into what I call the miscellaneous territory, meaning, the main concepts are naming, reactions, intermolecular forces and properties like that, which we'll talk about when we get more molecules than just alkanes to talk about. And so, those are the main topics. And then there's just all the other little topics that crop up from now and then. A lot of little vocab in there and things like that. One of those that's a little bit, that crops up more often than the other topics is the concept of isomers. And there's at least 3 types of isomers. And the first type is called constitutional or structural. And that's what we're going to have in chapter 19. And then the second type are called geometric, and sometimes they're called cis and trans, and there's other names for them too. We'll deal with those in chapter 20, even though you've already, unbeknownst to you, had them in the very first Lewis structure lab, and you also had them in the Lewis Structure Lab that you just finished up this week, that's when we have molecules with those carbon-carbon double bonds, right? And then the third type that we're going to talk about are stereoisomers, and they get their entire own chapter, which is chapter 27. I don't know, don't hold me to that. I guess I could page through the book. But they basically get an entire chapter on just stereoisomers. And so, you know, we're not going to talk about 2 and 3 at all because we're going to save those for the appropriate chapters. But we are going to talk about those constitutional or structural ones. You have a question? What's after that? Oh, geometric or cis-trans is what they're called. So it's kind of an or. Yeah, the idea is that there's 2 different orientations or more that we can have around, well, 2 that we can have around a carbon double bonded to another carbon. And just arbitrarily, one is called the cis version and one is called the trans version. It's kind of like we arbitrarily say one direction is left and one direction is right. We just have to have some way to distinguish between the 2 directions. We picked those 2 words. So constitutional or structural isomers are compounds that have the same molecular formula, but they have different structures, structural arrangements. And in fact, the thing that all isomers have in common is they're all going to have that same molecular formula. And then what's different about them, or what's the same about them, is going to change as we, talk about different types. But for now, it's the same molecular formula, different structural arrangements. An example of that, and probably the very first molecule that you can encounter it on, is if I take a look at just butane. That's 4 carbons, right? This is C4H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But see, I can also make another compound that has that formula C4H10 by simply rearranging the order that those carbons are in. And so if you count up the carbons and you count up the hydrogens on that molecule, that's also C4H10, right? So notice that they have the same formula, C4H10, but they have different structures. And because they have different structures, they also have different names, meaning one is called butane, one is called 2-methyl propane. A good way to check to make sure that you've sort of named all the isomers for a compound, or that you really have pictures that are different instead of pictures that are really the same, is to name them all. And so if they have a different name, then that means they really are different molecules. If they have the same name, then that means they're the same molecule. For instance, as an aside, I can draw butane like this if I want, right? Oops, maybe I better not have that many carbons. But that's butane, right? That looks different than that, right? But they're both 4 carbons in a row. They're all butane. I mean, I can draw butane like this if I want. There's probably 50 different ways I could try to draw just butane, the molecule. But they all have the same name because they're all just 4 carbons connected in a row, no matter what bond angle I try to draw or show in there. So one of the things I want you guys to get some practice on is naming and drawing isomers. And really, the whole reason for doing the isomers and making you do a question or 2 on them is simply that it's good practice for naming, so you get extra bonus practice. And it's also good practice for looking at a molecule and recognizing when they're kind of the same and different, and it's good practice for counting up the number of carbons. And one thing we should realize is that the number of isomers, the number of structural isomers increases rapidly with the number of carbons. And as far as I know, there's no pattern. So you can't predict how many structural isomers there's going to be. And I could be wrong on that. There might be a way to predict it, but it's awful hard if so. Some people, of course, have figured out how many there are. for instance, notice that with butane, with 4 carbons, I only had 2 isomers, right? So if I look at the number of carbons and the number of isomers. Now don't memorize this. All I'm trying to show you is that organic chemistry, one of the reasons it's a big field and one of the reasons it's a difficult field is that with just a few atoms we can have many, many, many molecules. It's kind of like how with just the periodic table we can have everything you see around us. That's pretty impressive if you ask me for, about 110 elements or so. So if I have 4 carbons, I've got 2. If I go to 5 carbons, I only get 1 more. 6 carbons, I get 5. 7 carbons, I'm up to 9. By the way, that's your homework example, or homework problem, I'm pretty sure. So you'll have to come up with 9 of them. If I go to 8 carbons, here's where, gotta be honest, am I gonna ask one with 8 carbons on the test? That'd be 18 molecules you have to draw and name? Probably not. If we pop up to 10, we're up to 170, or not 175, 75. If I go to 20 carbons, I'm already up to 366,376. Just 20 carbons. And most molecules in your body, most biological type molecules, have way more than 20 atoms in them. And this is just 20 carbons, meaning we haven't even thrown in nitrogens and oxygens and chlorines and fluorines and all the other atoms and elements that are possible. And so you can see that with just 20 carbons, that's 366,376 test questions right there. Now, we don't name anything over 10 carbons. You want to know the real reason we don't name anything over 10 carbons? My computer program can't draw anything over 10 carbons. Technically I can pay money and get lots more than 10, but heck, I get 75 plus all the other isomers. And if I just throw a chlorine on there, then I've got, another couple hundred molecules. And if I throw some cyclic molecules in there, there's 20 or 30 more. I got plenty of molecules to pick from for test questions. If you ever want to see the entire list of every molecule in the class, I'll show it to you sometime. It was the first, people thought I was funny. The second year when I realized that people needed practice on this, I sat down and I just started drawing all the isomers of everything and naming them on a piece of paper. So I have entire notebooks like this thick where I just went through and drew and named things. People thought I was insane for a while because I'd just sit in the meeting and they'd be like, "What are you doing?" I'm like, "Doodling." Anyway, sorry, got off topic. So, some rules for drawing isomers. Oops, for, not fro. Is you have to be systematic about it. And what we usually do is we start with the main chain. And what you do is you remove 1 carbon and use it as a side chain. So for instance, the example we already did, butane, what I did is I said, okay, my next molecule has to only have 3 carbons in the main chain, and then I use that extra carbon as a side chain. Now, if I number this so that we can talk about it, where can I put that side chain? If I put that methyl group on 1 and 3, does that make a different molecule? No. So I really only have one place I can put it, right? Now, what if I do the exact same thing for pentane, meaning I start with 5 carbons, and now I'm going to make a chain that has 4 carbons, and I'm going to number it. Where can I put those? Where can I kind of put that carbon that I ripped off the main chain and put it as a side chain? Okay, so Jess says 2 or 3. So if I put it on 2 versus 3, what do you notice? Yeah, one thing you should be careful of is, for a lot of molecules, draw that plane of symmetry and realize that if you put something on one side and the other, it usually makes the same molecule, meaning both of these are really the same, and so they're both 2-methyl butane. Now, I should point out that there should be 3 structural isomers for pentane. So where's the third one? So I've got 2. I've got pentane Well, I don't have any extra carbons, meaning I've only got 5 carbons, right? So if my chain has 4, so if you run out of places to put it, the next step is repeat it. Now instead of ripping off 1, rip off 2 carbons. So now my longest chain is 3, and here the only place I can put them is both of those in the same one, and so this is 2,2-dimethyl propane. And so now I've got my 3 structural isomers. So what if I do, for one last set of examples, hexane? There should be, how many did I say? That's 5. So you always get a freebie, meaning the very first molecule is automatically an isomer, right? Meaning, if I say, name all the isomers of this molecule, well, you get the freebie because hexane is the molecule, right? So you really only have to find 4. So what's our process? Right, and where can I put it on that molecule? I'll number them again just so we can refer to it. Where can I put methyl groups on that? Yeah, the 2 is different. The 3 is different, but notice the 4 is the same as the 2 if I just count from the other end, right? So this is 2-methyl pentane and 3-methyl pentane. So we're already halfway there. And one of the reasons I like people to practice with isomers, and you'll see it as questions on the next couple of chapters and on the test, is because it really does get you to start looking at the molecule as a whole, realizing when, if you number from the other end, it's the same atom, and lots of little things like that. So, yeah, now what do I have to do? So I ripped off 1. Yeah, so now I'm going to remove 2. And so that means that my longest chain is going to be 4. And so where can I put 2 carbons on that? Put it on the 2 and the 3, or the 2 and the 2. Anywhere else? But yeah, what do you notice about the 3 and the 3? Same thing, right? So we've got what? 2,3-dimethyl butane and 2,2-dimethyl butane.
Why are you removing 1 and then removing 2? Like, how do you not want to do that?
Well, that's what I'm saying. It's a systematic process. So if I'm trying to find all the isomers of hexane, well, when I have just 6 carbons, there's only 1 molecule I can draw. That's hexane. And so another way to draw something with 6 atoms is to say my longest chain is 5 plus 1 carbon is a side chain, because 5 plus 1 is 6. And then when I run out of, well, no, because if I just add a side chain, 1, 2, 3, 4, 5, 6, if I just add a side chain to this is C7H14, 16, whereas this is C6H14, meaning that to be isomers, remember, that part has to be the same. So I can't just add more carbons to something. I actually have to rearrange the way the carbons are connected together. I can never have more than 6.
So when you're counting isomers, the original one counts?
Always. That's an isomer. It's got the formula C6H14, meaning every one of these is C6H14. And I have to be honest, I'm glossing over that part a little bit. I highly recommend that you prove to yourself that they're all C6H14 by, say, going, well, there's 3 hydrogens, 3, 3, 3, 1, and 1. So let's see, 1, 2, 3, 4 times 3 is 12, 13, 14. Meaning that's a good double check to make sure you didn't draw something wrong. Because what if I do this? This is also 6 carbons, right? What's the formula for that? Each carbon here can only have 2 hydrogens, and so that's really C6H12. I do the math right. That was our least favorite student showing up late for the record. So, notice that, for instance, one of the things we can't do is make a cyclic molecule when we're making structural isomers, right? So the process for making these isomers is systematic, meaning take a carbon off, put it everywhere you can. When you run out of options, take another carbon off, put both of those wherever you can. When you get to heptane, you might be able to take 3 carbons off and put them wherever you want. Well, I'll tell you how many isomers there are. So I told you ahead of time that there's 5. So notice we drew 1, 2, 3, 4, 5. So you know that you can stop. Also, for instance, if we did try to go one more, if we went down to, we'd have to go to 3 carbons, right? And I'd have to add 3 carbons. Well, I can add theirs, but notice there's nowhere else to add a carbon, right? If I add it anywhere else, for instance here, well, that's really just this one over here that we've already drawn. And so at some point you really just can't take carbons and rip them off and put them somewhere. But I have to admit that probably the trickiest part about knowing whether you have all the isomers or not is simply being told what the final answer is. And I'm a nice enough person that I won't simply say, draw all the isomers of heptane. Instead, I say, draw 9 isomers of heptane, which is how many you should have. So when you get to 9, you should stop. If you come to 10, then you should say, well, something's wrong. Or if you get to 8, you should be like, damn it, I know there's one more, instead of missing the hard one. And then, of course, we can also have all sorts of other structural isomers. For instance, if I just take a look at this molecule, how many structural isomers of chloropropane are there? Yeah, there's just 1, right? Meaning that I can only have that molecule, because if I put the chlorine on this atom, is that the same? Yeah. Whereas, like, say, for instance, what if I do this? What if I have 3 carbon atoms and I want all of them for this is chloroethane. I was thinking ahead of my next example. If I want all the isomers of chloropropane, I don't know how many there are, but where can I put a chlorine on that molecule that makes it unique? I can put one here and get 1 chloropropane. I can put one here and get 2 chloropropane. Can I have 3 chloropropane? No, because if I stick it on this end, that's just the same as that, right? So we're not allowed to have it. And then you can say, well, I can rip off a carbon, right? But where can I put that carbon? Well, I don't have any choice. I either put it here and I've already got that, right? Or I put it here and I've already got that. Arguably, you might say I could put it here, but what's that? What's wrong with that? Yeah, chlorine just can't make 2 bonds, right? So, you can draw that picture if you want, but it's not realistic. And also, that reminds me, remember whenever you're doing all these things, in the back of your head, be counting. Be going, and saying, okay, did I violate any octet rules with this molecule? Now, I admit we leave off those lone pairs on chlorine, but you've been drawing these now for 2 semesters, or at least a semester a little bit, and now, so make sure you're not violating any octet rules. If I say, what's the formula of that molecule, you have to be smart and say, well, I know there's really a bunch of hydrogens also on this molecule so that I can complete everyone's octet. So this is really C3H34567Cl, right? So in the back of your head, always be running these double and triple checks. Every time I name a molecule, I have to say things like that. I have to do things like that to make me, be honest about it. Let's see, miscellaneous stuff. Not really. Let's see. We talked about haloalkanes. We don't want to talk about reactions, do we? No, that's a topic that needs to be done fresh. I want you guys to focus on names right now. Where's my miscellaneous section? I do want you to make sure you read the chapter. I've been trying to put a couple sections up on the website a day and saying, read these sections, it matches up with the lecture, right? And then there is going to be a bunch of miscellaneous things. Like, for instance, what's the difference between saturated and unsaturated hydrocarbons? Has anyone actually pulled the book out and read anything in it? Maybe that's your weekend goals. Because that'll help you refresh the information in your brain. And hopefully when you read the book, honestly, for large parts of it, if you're not nodding your head and going, I already know this, why am I wasting my time reading this? Then, you're not paying it, you're not doing enough in lecture, you're not, internalizing the lecture information. If you read the book and you're like, wow, this naming stuff seems all new, now I'm confused. You're not internalizing that naming stuff, right? Now, admittedly, when you get to some sections of the book, like, the word saturated versus unsaturated, if I haven't covered it in the lecture, yeah, that's going to be new, and you should be like, oh, yeah, that's one of those topics Jay figured is so easy that he can skip. So I'm going to cover it anyway just because we have a few minutes here, and, it's worth doing. So the difference between saturated hydrocarbons and unsaturated hydrocarbons is these have the maximum number of hydrogen atoms. And what that means is that, for instance, if I have a molecule like that, that's C4H12. So notice that follows that formula, C to the N, H to the 2N plus 2. Actually, 12 is wrong. 8, that should be 10, like that, right? C4H10, meaning twice as many carbons is 8 plus 2, because you get an extra hydrogen per end, right? And then unsaturated carbons have less than the maximum number of hydrogens. And what it really means is that they contain a carbon-carbon double bond or a carbon-carbon triple bond, whereas here they only contain carbon single bonded to carbons. And so, for instance, if we take a look at it and I just throw a double bond in there, then notice that that's C4H8, because making that double bond between the carbons, I lose a hydrogen, right? If I draw the Lewis structure, and that's probably the easiest way to see the hydrogens, and Jay's not so lazy that he won't draw a Lewis structure to help out. And then if we draw one with a double bond, in fact, maybe we should draw it like it really is, like that. And then I can have an H here and one down there. And notice that since I make a double bond between two carbons, that means there's two hydrogens that can't be bonded. And since this is also the one you guys had in your lab, you know that there's two structures for this, right? I can have both the hydrogens pointing up, or I can have one hydrogen pointing up and one hydrogen pointing down. And again, we're getting a little ahead of ourselves. Double bonds are really, the topic for chapter 20, but since the test is on both chapters at once, doesn't hurt to see them a little bit. What we're going to learn is that the difference between these two molecules is, we call this cis-2-butene. Notice that now it's an E and E ending because it has a carbon-carbon double bond. And this is the trans-2-butene. So this is an example of the cis and trans geometry that we're going to talk about, or the stereoisomers in chapter 20. And it's, due to the fact that that carbon-carbon double bond makes that molecule not able to freely rotate. Where else have you heard the terms saturated and unsaturated? Not just hydrocarbons, but think about probably your nutrition class. What was saturated and unsaturated in nutrition? Fats. And what was the difference between an unsaturated fat and a saturated fat? What? Yep. We're going to recover this stuff in your in the biochemistry chapters at the end. Alyssa?
What is that word? Is that
Contains.
I don't like compounds.
It's I'm thinking about Chinese today.
What about if it has like monster or something? So you
Is it considered unsaturated? Normally, when people are talking about saturated and unsaturated, they're not talking about things that contain oxygen, meaning just the hydrocarbon part of the molecule. So one of the things you'll notice is that in your biochemistry chapters, or in your nutrition, I should say, with Sarah, she talked about saturated and unsaturated fats, right? The difference between saturated and unsaturated fats are whether they had a carbon-carbon double bond or not in them. Now, there's a little bit more in that fats are not alkanes. They have an additional functional group on them. But really, the big difference between the two is that. And then you've heard of trans fatty acids, right? Now, you don't hear so much about the cis fatty acids, do you? But what do we know about the trans fatty acids? Trans fats are bad for you. You know, the big thing I see in labeling is everything says 0 grams of trans fatty acids. And I'm like, bananas never had fatty acids in the first place, but I guess they really don't have them either. So, you know, it's a legitimate, you know, tactic. But all of these terms that we're using in the organic chapters, saturated, unsaturated, cis, trans, all that's going to pop up in our regular organic chemistry chapters too. Or I'm sorry, in the biochemistry chapters too, meaning the vocab in this is very important. Now I have to admit, we might not say the word saturated and unsaturated for 6 chapters, but I'm still going to expect you to remember it, you know, 7 or 8 chapters from now. So, you know, stick the back of the thing, or that in the kind of the back of your mind. When we talked about that this is C3H8, and then the next one is C3H or C4H10, can you guess what the next one is going to be? Yeah. What did we call that earlier? We talked about this on Monday, actually. You may not remember it, but it's a vocab word in there. These are called homologous series, meaning that they follow a pattern and that we can use that pattern to kind of, you know, make statements about the molecules. I think we'll just end here today. I don't want to overwhelm you, because what I really want you to do, and I'm going to give you the time, meaning, you know, we're not going to start another hard topic like reactions, because I want you to master naming this week. Or, since it's Friday now, this weekend. Meaning, you need to make sure that you come back on Monday and you're masters of naming. Because we're going to start in on reactions, and that's going to be tough. And then we're going to move into chapter 20, and you're going to name 3 more sets of molecules. So if you don't have the naming down from this week, when we do the naming next week on, say, the second half of Wednesday or on Friday, then it's going to be extra hard, because now you're learning stuff that you should have already known. And that's what's going to happen from now on. Every week we're going to learn how to name 2 to 4 more sets of molecules. And you're going to be learning a bunch more reactions. And so, like I said, if you master the rules right now, then the minor changes to the rules that we make with, say, carbon-carbon double bonds and carbon-carbon triple bonds isn't going to be much. Like, for instance, does this name kind of make sense to you? Can you figure out what all the parts mean? Meaning, what's the 2 telling me? Yeah, where the double bond is, because I could have the double bond here, or I can have the double bond here, right? So one is 1-butene, one is 2-butene. What is that? Cis is telling me whether it's up and, like, whether the main chain is both parts are down, or the main chain one part is down and one part is up. So you're going to be picking up on all this, but, like, for instance, if I drew this molecule, whoops, even though it's not in this chapter, do you think you could name that? At least take a pretty good stab in the dark at it. Meaning, you can say, I'm going to number the molecule, right? And I'm going to go 1, 2, 3, 4, 5, because we're going to learn that functional groups should always get the lowest number. And then that makes this a 4-methyl. And so, you know, this is just 4-methyl. You already saw that we have to tell where the carbon-carbon double bond is, right? And we know that 5 carbons is pent, right? And I told you that E means that there's a carbon double bond. So that name shouldn't surprise anyone, should it? And if I wrote the name for a molecule with a triple bond that has a Y-ene ending, it's not a big difference. So realize that if you can master the rules for that we talked about this week, then just changing the ending isn't going to throw you for a loop.
So for the double bond, you write the lowest number that the double bonds, or
The double bond has to get the lowest number. And like I said, we'll cover those rules in chapter 20. What I'm trying to say is master these rules now so that when you come to chapter 20, you're only learning one new thing, which is the double bond has an E&E ending and it gets the lowest number. Maybe that's two things. It depends on how you count. I'm not very good at counting anymore. No math in this chapter, so we don't count anything. So, before we quit, we should say homework 19D and F is due Tuesday. Meaning do them over the weekend, bring any questions you have on Monday. The other thing I would like to talk about at some point is I have my office hours honestly set Tuesdays and Thursdays at 9:30. How many people have a class Tuesdays and Thursdays at 9:30? Yeah, and I didn't set my office hours purposely there so that you guys couldn't come, because I realized that no matter where I put my office hours, no one can come to them. And so when times start to get tough and you guys want to start coming in and asking questions, feel free to come in at any time, right? But we probably should pick, maybe if you guys want to pick an evening time or something, because how many people have evening classes on Tuesdays and Thursdays, is it, or Mondays, Wednesdays? Monday, Wednesday. How late do you guys go? 8:30. That means when we put tests on Thursdays or Tuesdays, no wait, yeah, Tuesdays and Thursday tests means it's a little rougher because you have to go to class, right? We'll have to see how that goes. But what we'll do at some point is let's pick some office hours and some practice. I don't know if evenings still work for people or not. Yes, no, maybe, maybe not. We will make things after 6:15 because we realize athletes have their study stuff.